So thinking about the option I suggest for you, okay, for makeup the day of April 29. So you have to tell me your opinion from your side. I mean the best choice from your side or from HCMUT side. My option will be the two Saturday, um, May 15 or 20. Either either the Saturday May 15 or Saturday 22nd. Yeah. If not, then we have to use the extra which is not good because very far away from, I mean, because we start late by the COVID. So what is the last choice, you know? So this is three options: 15, 22nd, or 25th of May. So I refer you choose May 15, the best choice. Okay? From my point of view. But you have to confirm me early on class. So that I can inform to the OISP. They will need information to arrange the classroom for us. Okay? So you can send me an email after you discuss together. And right now I have to start the lecture. Okay? So we start chapter 9. We discussed about connectivity in the graph. Hoàng Nhân came very late. Huh? Should be here early, Hoàng Nhân. I mean, I asked the opinion for entire class, so I mean not asking about the makeup day for individual. I need to know the entire class, so that means you have to discuss together and tell me the final decision from your side a whole class. Because right now I got the reply from Hòa. He said, okay, but this is just his own opinion. I need to know the whole thing, so you have to tell your leader. The classroom leader will reply to me, okay? You can send email directly to me. This is my email address at my university. As soon as possible because the USB need that information. Okay. So I finished the discussion about that. I have to start the lecture right now. Okay. So let me think. We are talking about connectivity. So this is the longest and also most complicated lecture for entire course. So lecture number 9 target at least 3 learning outcome. As you can see from here, we need to employ the fundamental concept of draft to study the connectivity. Okay, then the connectivity is very important in modeling practical problem. Employ the district structure. Then there are some algorithm and some method. I mean optimization method to help you to operate to compute something on some models you obtain from district structure. Okay. So we have to go fast now because this is a 9:15. We kick off the study of connectivity by defining the path and the circuit. And to study number 2 here, we need to review about the connectedness for the case undirected graph. I mean, when we define graph theory, we mentioned that earlier in lecture number 8, but today we review because we have some new result from that. Then we study the Euler and Hamilton path, very important from application. Then we enter the one of the basic problem in graph theory, namely to find out the shortest path. Okay. To do that, we need to define the weighted graph, and there are a lot of algorithms, and I choose only the most 3 well-known: the Dijkstra, the Bellman-4, and the Floyd-Warshall algorithm. Then we apply to some application, and finally we define the concept graph color and discuss how can we color the graph. So let's see the picture. Okay, I give you this undirected graph having 6 degree or 6 nodes, A, B, C, D, E, F, and we assume we are starting some journey from the node A, like this one. Then we can choose the next node on your journey to be vertex D. I mean, the graph is undirected graph. So after I have chosen some new vertex on the journey, then I put the red color, and I also put the arrow on the red color to indicate the direction of your journey. Okay, your visit or your trip. So after the vertex D, we move to vertex C. I mean the new not much extended from the current one. So after node C, because you have connection CF, so you can move continuously to the node F. So after F, we can go back to E, not E. Then, well, we can say, okay, we arrive in your countryside home, for instance. If we assume that A will be your home in Ho Chi Minh City and E will be your second home in countryside. And in this case, any component of the trip, namely AD, DC, CAF, and FE, in total we employ 4 connection or 4 edges, and each of the connection we employ only once. So I give you the first concept, namely symbol path, and the path to have 4 connections. So we say the path of length number 4. You see. So this is the first example about the concept. but we can do something else. Let me show you. So in the second example, I will choose the starting point will be not B right here on the same graph, but we try to draw the second trip. We go from B and to C, and then from C to F. I mean, by similar idea before, but the beginning point now will be small b. After F, we go back to not E. You look to the blue, and after not E, we get back to the original not B here. So we get the last connection. All right. So lost connection. Now can you hear me? Guy, can you hear me? Yes, good. Can you see the slide? Can you see the slide yet? The slide, the presentation. Now, can you see the slide? I turn on the slide for you again. Can you see the picture? There are two. So see the graph, huh? Yes. So you look to the second one, the blue one here. Good. So the blue one consists of also four connection, but we start from not B and we stop also at not B. You see? So in this case, we start from B and we go back to B. Somehow you can write in this way as a sequence of node inside the graph. After the node E, then we go back to node B. Where in the first graph here, you start from A, but you stop at E, and E not equal to A. So we have the symbol path, but now we have a circuit. So a circuit is just a path where the beginning and the ending node are the same. We start from B, we get back to B. So that is the concept of circuit. The length should be number 4 because you employ 4 connection: BC, CF, FE, and EB. So this is the formal definition. We define the path of length N from beginning node U to ending node V, a sequence of the connection. Okay, so here we did not S0 to be the beginning U, and we did not Sn here to be the last node V. You see, so we have a connection from S0 to S1, S1 to S2, etc. Like you see in the picture. You see, you cannot start from A, no, and you move to F. This is impossible because in the graph you don't have the HAF, but you have the SAD. So that's why we say the intermediate node inside must make an H. Okay, Then the path we're gonna circuit if the beginning and the last point identical together. And finally, we have the path to be symbol or a circuit to be symbol if one connection appear only once here. In other words, if the path does not contain the same edge more than once. So we allow only one connection appear in the path, in the symbol path. Okay, symbol mean single connection allowed in the path. So A, D, C, F is good example of the symbol path of plan number 4. Okay, and look to the right hand side picture, and we also start from A, but now we choose another journey. We go to the right, but not A, go to B, and B to E. I mean, we define a new trip from not A. So after E, we go back to D, and from D, we go back to A. So the second right picture show you a circuit. The left hand side is symbol path, but we not yet finished the trip. You see here, after get back to A, we continue to go again to not B. That means the connection AB now appear 2 times in the new trip. So we start from A, but we finish at B. So the second one journey, we can say A, B, E, D, A, B. So we finish at B. Therefore, this one, the connection AB appear 2 times. So this is a path, but not symbol, because that violates the definition from here. Okay, the left hand side is good because only one edge appear in the path, but in the right hand side, the connection AB appear 2 times, not allowed in symbol path. So we define the symbol because we try to avoid the complication by using many times one edge. So I recall the definition of connected. Maybe you forget. So you are given undirected graph and the graph G. Let's say, so we can say the full graph here to be the graph G, and this one we call connected. If, by definition, there is a path between every pair of distinct vertices, okay? So every pair, so it must be true for every pair. After you choose the pair of vertices, then you have to draw a path, connect them. So if I start, let's say from AD, okay, then I choose the pair DH, and you have to show me a path connect D and H. You go through E perhaps, F perhaps, G, and you go here. But if I give you, let's say, not E and not B, so, well, in this case, this is a good example of connected because you see that any choice of pair vertices, you can find out the connection or the path connecting them. Okay. Inside a connected graph, maybe sometimes the path consists more than one connection. I mean, one edge appear 2 times. So you can simplify to get back to the symbol path. I mean, the path here by definition can be either symbol or not symbol. And then after that, you can choose the symbol, okay? If you know that the graph is already connected. So look to this picture again. Before, this is original graph, you see. losing connection the second time. So very bad communication today. So be patient. Be patient, please, because this is out of control from our point of view. You know, this is in intercontinent communication, inter countries connection. So depend on so many uncertainty. I think that the connection destroy the presentation, so I have to recover that. But do you hear my voice, right? Still, right? My voice. So the graph here is connected phi by this definition. Okay. Now assuming that if I cut, let's say, the connection CD, and somehow if I cut that, after cutting that connection, then the vertex on the left here, ABC, now cannot connect to some point on the right hand side like the node F. You see? So therefore we conclude that if we delete out the connection DE, or actually not DE, CD, sorry. If we delete the connection CD in the graph, please follow the picture I draw there for you. Okay, this one. Then after that, somehow you get two different graphs, the left hand side by ABC and the right hand side by the other vertices. And any point from here, let's say A, cannot connect to node F on the right hand side, and in that case we have disconnected graph. So I will show you in the next picture. Now you see, because you don't have connection CD, but furthermore I also delete the connection EF as well, EH. So somehow the new graph is disconnected, and we get three different components like this one. This is the first component, this is the second component, and this is the last component. So the new one disconnected, and we got three smaller components inside the original one. Okay, the original one lost two connections right here, and it's decomposed. So I draw this one for you. So somehow we have three components here, and we call that one connected component. And there are three connected components in this picture: G1 on the left, G2 in the middle, and G3 on the right hand side. Compared to the original draft, where we already had this one, it was connected, but now because losing the two connection here, then we get three disconnected components. So we talk a little about the disconnected draft, very important. We start here, the definition of connected. You say that for every choice, every pair of nodes, we formalize by ij inside the original vertex. Then we only can find out about, connecting ij. Then if you want to know the concept disconnected, you have to take the negation. Okay, you consider the first definition here is predicate A, and then this one will be the negation of that predicate proposition, namely. So disconnected means negation of the original one. Okay, so in the original one here you say A here, the original one. Connected means for every choice of pair. Now disconnected means there exists. Okay, so there exists specific node inside the graph so that no path connecting them. Okay, in the second case, we already mentioned in the previous figure that the original graph G now will be reduced to smaller. We call subgraph G star, and there are so many subgraph inside G. Okay, and each component like that we call connected, and inside each G star, I mean the subgraph or the connected component, the subgraph is locally connected. I mean connected inside its own. You know, the last figure show you three picture G1, G2, and G3. But now we generalize here to the zero case, assuming that after you get disconnected graph and we have in total P connected component, we divide them by G1, G2 up to Gp. The last example, actually we got the last example show you the case where the value P exactly number 3, but in general we allow any value P bigger than or equal to at least number 2. So the last figure show you 3 connected components. Now we would like to talk about the relationship between the original one and the connected component G1, G2 up to Gp. You can represent in this way. Okay, first of all, I will denote each connected component Gk, where in this case go from number 1 up to number P, because each one like this to be a subgraph, so you can write the vertex set of that component by Vk and the edge set by Ek. Then we conclude that we get the decomposition of the original graph by many components G1, G2 up to Gk, like that one. And we symbolize that relationship by writing this equation. Okay, this is the left hand side, disconnected already, and this one consists of many P connected components. In the sense that the notation right here mean we take the union graph of Gk and Gh. Okay, union graph mean we take the union of the vertex, and you also can take the union of the edge sets. Okay, continue. Oh, not audio. Now you hear again. Hear me again. Yes, okay. See me. Can you see me? Okay, good. So the last figure show you three connected graph, and we would like to symbolize that connection here. So in general, we have P component, and each component I can write by notation GK like this one. GK will be a subgraph. Therefore, you can write GK in this way. And then let's say G1 and G2. So GK to be number 1 and GS to be G2. And we talk about the union graph by taking the union of the vertex set, okay, V1 union with V2, and also we take the union between the edge sets. So we understand this notation like the union, okay, union of the two connected components. And because we have P connected component, therefore we have to write the graph G, disconnected graph G, to be the union of many components in this equation. Okay, so this one we call the decomposition of a disconnected graph by using the component GK. So in the last picture we have G equal to G1 union with G2 and union with G3, and we don't employ the notation union of the set like this one, because this one apply for the subgraph. Okay, so the union here mean union of both vertex set and also union of the S set. The end of chapter 9, we have a very important exercise about that. Okay, now talking a little more about the connected here, I give you this one to have in total 8 vertices already connected, you see. And if you choose, let's say, some point like some node like A, and if you delete this one out from the original graph, then somehow the remaining here, after you delete out the node A, the remaining graph still be connected, you see. But what if we don't choose A, but now we choose the node B here, okay? And we also considering, cut the node B out from the graph here. Then you see when you delete node B, then this one will disappear. That one disappear because the node B already disappear, you see. Then after that, how many components do you get after I delete out node B? Tell me, okay? How many components we get? And you see very clearly that after you delete like that, then the node A still be inside. Okay, and then the second part consists of everything on the right hand side. You see like this one. So the number of connected components turn out to be number 2, right? Because this one is isolated, is a subgraph itself, and the right hand side will be the second one. But somehow we get original one connected, and after you remove this one, then you get disconnected. So we define some name for node B. We call that cut vertex Okay, not B is called cut vertex or articulation point. Draw in the picture like this one. If and only if removing not B will disconnect the graph. So you see clearly in the picture here. After you remove out not B, then you get exactly the number of connected component will be number 2, which is bigger than number 1. I mean, when small b bigger than 1, then we say the graph G is already disconnected because the number of components bigger than 1, you see. So the not B, we call the cut vertex because that like this one. Okay. Now we define the concept cut edge. We employ the same graph as before, like this one. You see, I ask you, what if we remove the last right connection like here? Remove this out. After you remove this, but the node G and S still be right, not removed yet. So after you remove that, then the remaining, the result graph turn out to be a new graph like this. After you remove out, okay, then somehow the outcome still be connected. So the connection here from G to S is just a normal a normal edge, but there are some more important edge like the connection AB. You see that if you cut out AB, then by the previous example, you see that this one become isolated, and this one make a component itself, where the right hand side here, I'm talking about the second case where you remove the connection AB, then the outcome will be disconnected. So there are some certain important edge, while the other one not so important. And the one important, similar like AB, like this, we call the cut edge. Okay. So the cut vertex and the cut edge are something important than the usual, the normal vertex or the normal edge, because they disconnect the graph. In some textbook, they call the cut edge to be the bridge as well. In that sense, the bridge, like this one is the bridge, okay, but this one is not. No, this one is not, because you cut AB, then the connectivity is invalid. Okay. So I cut. You see, I cut this one. And after that, you see, we have seen clearly there are two connected components. So this one we finish right here. Okay, delete out one connected component, and the right hand side is the second connected component. Long time ago, the the transportation system from Mekong Delta to Ho Chi Minh City depend uniquely on the bridge in the bridge we call Bình Điền bridge, or Tân An bridge, and assuming that one will be this one, then by some certain region, unluckily the bridge were destroyed, then you cannot go from Ho Chi Minh City to Mekong Delta. So that's why you see the name bridge here they mentioned. But in Ho Chi Minh City itself, there are a lot of bridges, a lot of edge, a lot of connection. If you remove, let's say, the bridge Kamet in District 1, connecting from District 4 to District 1, you see, Kamet bridge, then if this one is destroyed, then you can still go from your home in District 4 to center of Ho Chi Minh City, because you can employ other bridges, like Nguyễn Phương bridge or something like that. So we classify the important role of the vertex and the edge by putting adjective cutting before, like this one. Now, a little further, we define the concept vertex connectivity and edge connectivity. If the graph does not have cut vertices, I mean does not have, we say in Vietnamese, like this one, we say non-separable graph. If the graph does not have cut vertex, then I mean in either way, like this one, if I delete this one out and by default this one disappear, that's okay, and this one also disappear as well because it's connected to A. Then after that you get a new graph consisting the right hand side I am drawing now, and this one still connected, so A cannot be cut vertex, and by the similar idea, B also not cut vertex, G also not cut vertex. So that means the graph here does not have any cut vertices. So this graph is a perfect example of the concept non-separable graph. So from that observation, we can define the next one here, the next concept here. We call the vertex connectivity. So I don't choose A and B, etc. But now I choose both of C and F. Let's see what happens. If I choose both C and F, you see, before we get the original one, and I remove both of them at the same time. Remove this one, and also remove this one. So that means every connection to C and every connection to F also disappear. So that means after you remove this one out, then the new graph now consists only two connected components, one on the left and the other one on the right. So that means if you put C and F together, C and F together, and you remove them at the same time, simultaneously, then obviously the graph G now disconnected because this gives us the left hand side connected component, the right hand side also connected component. I redraw the outcome on the right hand side here for you, you see? So because at beginning C and F here, but now they disappear. So you get disconnected already, and this is one component and this one the second component. So although we conclude that the original graph does not have single cut vertex, but if we merge them together like that one, then they can make the graph disconnected. So we define the concept here. Vertex connectivity will be a number. So that is the minimum number of vertices you can put to be the vertex cut. So in this case, you see the vertex cut to be a set, okay, consisting of two cut vertices, and you need to make the graph disconnected. You need to put at least two. So that's why we call this one to be the minimum number. That means if you put more, like you delete also this one, obviously the graph strongly disconnected. But we don't define that number 3. We define the minimum number of element inside a vertex cut. Okay. So a cut vertex is a node, but a vertex cut is a set. Okay. In this case, the cardinality of this one to be number 2. Okay. And that number we call kappa G. So that notation we call kappa G. We call the vertex connectivity. And by the same idea, we extend the cut edge to the edge connectivity by the same idea. So you remember this lecture, we have more than 50 new definitions. You have to be very careful because the definitions are different. They are not the same. Okay. Now we want to define the edge connectivity by the same idea. If you want to disconnect the draft, if you delete only one connection like this one, not strong enough, not enough, okay? So that's why in this picture I remove the connection BC and GF and AF at the same time. I remove in total 3 connections, because if I remove less than, then the graph still connected. I would like to disconnect the graph. I remove 1, not enough, okay? I remove 2, still not enough, because the node D still, you know, can go to any place in the graph. So therefore, in this example, I choose number 3, connection BC, GF here. Why not number 2? Because you imagine that by the same idea, if I did not delete, I remove out only BC and GF, you can go from A to the internal part here. You can go from A to the internal part here by going through this connection, although you delete the 2 here. So that means delete 2 not strong enough. You have to delete 3 connection. I delete 3 connection, BC, GF, and AF simultaneously. Then obviously after that, the trap will be disconnected, you see, by observing here. And we define that one to be the edge connectivity by the same idea like we define here. So we need to formalize the edge connectivity as well, you see. After I cut the 3 connection, then I got the trap disconnected clearly, because the BC disappear, the GF disappear, and the AF disappear. Therefore, you get 2 separate parts, 2 separate components. So we formalize that one in the definition here. You see, the edge connectivity in Vietnamese like this one. This is a number we call lambda G. The vertex connectivity we denote by kappa G. The edge connectivity we denote by lambda G. And again, defined to be the minimum number of connection in the edge cut. So in this case, we need to remove at least 1, 2, 3 to make the new graph disconnect. So lambda G will be number 3. So the graph here show you 2 cases to illustrate the idea. And both of the cases defined to be the minimum number of some certain important vertex or connection. They are a natural number, of course. So the vertex and edge connection very important in computer network, because you want to make sure that the computer in your company, you know, large company like Ho Chi Minh City University of Technology, there are a few thousand computers, and if we talk about the reliability of the computer network, then you have to make sure the number of connections must be very highly reliable, okay? So you have to make sure that this one and that one must be big enough, you see, by the concept vertex connectivity and edge connectivity before. And the same idea apply for the transportation system in any country. I mean, not only in Vietnam, in Thailand, Malaysia, but let's say, well, in Europe or in America, in European country, then you have a lot of highway, etc. And to make sure that the flow of commodity, the car, the truck, the motorbike, you know, are moving smoothly is in the national highway system. You have to make sure that the number of intersection, that means the cutting point, okay, the vertex and the connection here also must be large enough. So really speaking, the kappa G and the lambda G must be large enough to maintain the reliability of the entire transportation system, okay? So any practical things can be modeled in draft theory. So this is some application of that. You have to understand the abstract definition because we will employ that when you design algorithm in the future. Okay, so we summarize the disconnected theory here via this very basic result. This provides you some quantitative connection among the three important parameters of any graph, namely small n, the number of vertices. Second one, parameter m, to be the number of edges. And finally, the one we learned today, yesterday, the number of connected component, small p. So remember, in any undirected graph, we have three important parameters to remember and to employ. The number of vertices denoted by n, the number of edges denoted by m, and the last one newly defined today, the number of connected components. Look into the chat box. And this theorem, well, we can say theorem 0, okay, because this fundamental rule, we don't count number 1, number 2. Let's say theorem 0. We talk about the relationship among the three parameters n, m, and p. Okay, this theorem regards the decomposition of the disconnected graph, and we always came through the two mathematical constraints, or we can say algebraic constraints on this one. We provide a lower bound of m